let's do an exercise on sigma algebras. So this will be an exercise. So here's the exercise. Prove that for any family, so a family in this sense is just a set, any family of sigma algebras, so I'll write script A, capital A, subscript alpha, as alpha ranges over some index set, capital I. So this is each element of this set, this family. I'm just calling it a family, not for any good reason. But so each element of this set is a sigma algebra. So A alpha is one of those. Prove that for any family of sigma algebras, A subscript alpha, the intersection, let's write it as just A. It's the intersection over all of these, over all alpha in the index set. And so this index set here could be, it's just arbitrary, not necessarily countable. Could be finite, could be countable, could be uncountable. Just some arbitrary index set here. Over all of these, so the intersection of all these sigma algebras is a sigma algebra. All right, so, and these are all on, of sigma algebras, let me say, on some common set omega, some common space. All right, so this is the exercise, and I would encourage you to try to do this on your own before watching the rest of the video. And if you do decide to do it, I would recommend, if you get stuck, then play a little bit of the solution, and then pause it again and try, keep trying, and then if you still get stuck, play a little bit more, and so on and so on. And so then that way you'll be able to learn it better. All right, so let's see how we can prove this. All right, so now if you're going to try it, pause it now because we're about to start. Okay, here we go. So the first thing to get your head wrapped around is what this object is here. This is a set of sigma algebras. So it's a set, and each element of that set is a sigma algebra. So each element of the set is itself a set, right? A sigma algebra is a set, and it contains sets. So this is a set of sets of sets. So you need to get your head wrapped around that, and build up some mental machinery maybe to keep track of all the things that are flying around here. Okay, so once you get your head wrapped around what that is, the first thing we need to do is to verify that this is a sigma algebra. First, we need to check that in fact it is a collection. So we need to check that it's a collection, just the basic thing. A collection, this is just a set, a collection of subsets. So I can just write it this way. We need to check that A is contained in the power set of omega. Just the basic thing. And so for any element of A here, if you want to show that something is a subset of another thing, you say, okay, take something over here, so let E be a member of this, and then we need to show it's in this side. So if E is a member of the sigma algebra, then so before I continue with this, let me just give you a side note here. The intersection of something, right? The intersection of all these, something is in the intersection if and only if, so E is in the intersection if and only if E is in script A sub alpha, if and only if it's in each of them. That's for all alpha in I. I'll just put for all alpha. You know it's all alpha in this index set here. Just for shorthand, for short. So this is just what it means for something to be in the intersection. That's just what it means, right? That's a sort of a definition. That's just an aside. Alright, so this is what it means to be in the intersection. And so E is in the intersection. That implies E is in A, that's the intersection. That implies that it's in each of these. And if E is in one of them, say, for any one of them, then it's a set, it's a subset of omega, and so it's a subset, so it's an element rather of the power set. So I guess actually I should, to be precise here, I should say this is a non-empty family. To be clear that there's at least one sigma algebra in here. Because if there was no sigma algebras, then the intersection would just be, it would be nothing. It would just be the empty set. So yeah, so we need this condition. Sorry if you got stuck on that. Okay, so this first thing is verified. That's just the basic thing. So we have this. Check. Now the next thing is we need to check that A is non-empty. So we want to say A is non-empty. So we'll put a question mark. And to check this, let's see. So omega, we saw that any sigma algebra contains omega, the whole space. So omega is in A alpha for all alpha in I. And by this, just the definition of the intersection, that implies, since take omega to be E here, that implies omega is in the intersection of all of them, which is just A. So that means that A is non-empty. It contains at least one element here. It contains the element of this set that is this set omega. Okay, so right, you have to keep track of every, this is a set here. It's omega, but we're thinking of it as an element of this intersection A, right? Okay, so we got that one. So check. Number 2, check. So right, so that implies in particular that A is non-empty. Right. All right. Number 3, let's see, what else do we need for sigma algebra? Let's see. Oh, right, we need it to be closed under complements. So is it closed under complements? Let's see. Let's make a little more space here. Okay, so how are we going to show this? Well, so let's let E be an element of, so to show it's closed under complements, we need to show that for any set E in A, we need to show, so our goal is to show that the complement is also in A. So if we can show that, then it's closed under complements. So E is in A implies that by the definition here, right, this intersection, this is A for us. E is in A implies E is in, so I'm assuming if and only if means this implies this and this implies this. Okay, so just get that out of the way. So E is in A implies that E is in each of these. So E is in A alpha for all alpha. And each of these is a sigma algebra So for any alpha, E complement is in A alpha because it's closed under complements, and that holds for all alpha. Just one of the properties of a sigma algebra. You know this property, but for each of the individual ones, which we are assuming by our assumptions, these are sigma algebras. And then again, using just this fact, taking this E complement over here, that implies that E complement is in the intersection, which is A. And that's what we wanted to show. We wanted to show that it was closed under complements, so that gets a check. And the last thing we need to check is that it's closed. Closed under countable unions. So for this, we need to consider a sequence of sets, E1, E2, and so on, all in A. And we'd like to show that their union is also in A. So let's see. How are we going to show that the union is in A? Okay. So we use just this condition here for any given k. So for any one of these, so for any integer k, 1, 2, etc., ek is in A, right? And therefore, ek is in A alpha, and that's for any alpha. So that implies that, so right, for any alpha, we have that all of the EKs are in that A alpha. And so since that A alpha is a sigma algebra, then that means that for any A, the union, let me make a little space here, the union over all alphas, maybe I'll put alpha in, well, you know, it's over all alphas in, or no, not over alphas, this is over k, sorry, from 1 to infinity. The union of these is in A alpha, because A alpha is a sigma algebra. And therefore, using this with, so right, we take the union of all the E's is in A alpha for all alpha, and that implies that the union is in the intersection. So the union, that implies the union of all the E's is in A. And that's what we wanted to show. We wanted to show that the union, that this was closed under countable union, so the union was in A. So we got it. All right, check. So that shows that for any non-empty, sorry if this threw you for a loop here, for any non-empty family of sigma algebras on this over the same space omega, over the same set omega, the intersection of all of them is a sigma algebra.